Hi, my name is Adi. I'm a graduate student at MIT. In this lecture, I'll be telling you about heavy quark effective theory with top quarks. So in your heavy quark effective theory lectures, you learned how this theory can be used to describe mesonic systems with a heavy quark, for example, mesons with bottom quarks in them. And you learned that this theory is useful in the regime where the mass of the heavy quark is much bigger than the non-perturbative scale. So this is about heavy quark effective theory with top quarks. So top quarks are special. So top quark is heavy. The mass of the top quark is about 173 GeV. But top quarks are special in the sense that top quarks decay before they hadronizes. The decay width of top quark which is bigger than lambda QCD. Hence, top quark never forms a meson. So in this case, how are we going to do heavy quark effective theory? So the question we are trying to address in this lecture is how to address width effects, how to include width effects in my heavy quark effective theory. So let's first draw a diagram which for the propagator of top quark, but now we will include the electroweak corrections in it. This propagator will have a value given by this formula. So this propagator leads to a correction given by sigma. We learned that the real part of sigma gives corrections to the mass term. But by optical theorem, we also learned that the imaginary part is related to the total width. Which can be seen as taking a cut of this diagram. So using this idea that the correction to the propagator is an imaginary correction, and one can use optical theorem to describe it, one can do phenomenology for top quarks. So the examples where it's relevant. Let's say we consider E plus E minus to TT bar. We can have two scenarios where the energy of the center of mass is order 2 MT, or where the energy is much bigger than top quark mass. The first regime is called the top quarks production at the threshold. And the effective theory relevant for this energy scale is non-relativistic QCD. And for this case, one uses soft collinear effective theory and heavy quark effective theory. We will focus on how heavy quark effective theory can be modified to account for width effects. So the Lagrangian for top production, for the Lagrangian for the tops, including width, is given by this. You're familiar with this part. where this part is the correction to the mass term, and now we have included the width effects. And this I gamma t over 2 term, this accounts for all the electroweak corrections coming from top quark decays. So if top quark has a momentum p mu, it's written as p mu plus k mu. And now from this Lagrangian, we can write down the propagator. Now instead of I0, we have I gamma t over 2 term. Power counting tells us that these 2 terms have to be of the same order. Phenomenologically, what that means is that top quarks are produced near the peak, in the peak region, which I can also write as the momentum of the top or the decay products is such that this is of order gamma t. This can also be defined, I'm going to call this S hat, and we observe that if I square this, I get which has to be of order gamma t. To describe production of top quarks, we can look at the cross section. Now this cross section will have both real and virtual corrections, and I've drawn double lines to indicate now we are working in the heavy quark effective theory regime, where the double line describes the top quark. But now after including width, we have also included all the effects of top quark decays in this. We can have corrections such as these ones, which would be the virtual corrections or the real corrections, and they can now be studied using heavy quark effective theory. So if so the cross section will include contributions of this type, which in turn looks like this. And hence, we get the well-known Bright-Wigner. So the Bright-Wigner is now part of the cross-section, which is nicely accounted by the width term. But now, this is the tree-level result. But we're using the HQET Lagrangian, we can also calculate the higher-order corrections, which for the graphs which look like this. These graphs will be the higher order corrections, and they will now modify the Bright-Wigner to include order alpha as corrections. These two graphs can be accounted for the Lagrangian. This graph, however, comes from a Wilson line, which you will learn about later in the course. And as a side fact, one can also see that one can also understand why schemes such as MS bar schemes are not good schemes for doing top quark measurements, top quark mass measurements. That would be because the delta M because of power counting, has to be of the same order as gamma t. ms bar mass for top quark is the correction from ms bar is actually much bigger than gamma t. So we need to work with schemes which are of order of same gamma, which are of order gamma t.